Hi, my name is Matt Bemis, and I support CFD here at Autodesk.
And this is Marwan Azzam, also in the technical support team here with Matt. And welcome to our webinar today, which is the part 2 of our electronics-focused webinar for CFD.
Right. So part 1, we kind of talked about how to define parts inside of CFD, how to accurately assign material properties and how they affect the model. We kind of went ahead and implemented those and really want to focus on running models here and getting good results. All right, so the content of today's discussion. We already had the CAD model that was simulation ready from last webinar. Now, basically, we put a bounding box on it and add an inlet and outlet extension in order to make sure we get good results. We touch on meshing, what you need to mesh, what you don't. There's a bunch of different options and pros and cons there. And we talk about how to set up the solve dialog box, what's important to get right and what is not so important. Touch on energy and mass balance because it was actually a struggle for me for a while. And I know a lot of people kind of get confused there, and it's a pretty easy subject to touch on there. So, and then we kind of did like a parametric study. So this was me trying to play the role of a design engineer where your design question is, what's the highest inlet temperature at the inlet of the fan that this thing can operate at without chips getting way too hot, and what's the criteria for chip temperature there. And after that, Marwan is going to touch on basically a natural convection recap. My model, as you guys probably know, is forced convection, but setting up natural convection analysis is not very intuitive. It's probably harder to get right than forced convection. So he's going to run through some awesome results there, and that's pretty much it for what we have to share. All right, so we already had the CAD model. Basically, I had to add a bounding box, which just means you kind of define your fluid domain. So here it was an aluminum housing of the electronics box that we put on there that just covered, rectangular box that completely enclosed the electronics. We also added inlet and outlet extensions. Sometimes people aren't too sure why you need inlet and outlet extensions. A lot of people ask, how long is in length is long enough? And it's really to ensure that there's no recirculation across the inlet or outlets, which can cause A, really bad results, and B, it stems from mass imbalances. So there's no perfect answer to how what's the perfect length of a inlet or outlet extension, but I started with 5 times the diameter or 5 times the cross-sectional length on that rectangle. And really what you have to do is check the mass balance going in and out, and if it's bad, then you have to add some length there. So the mass balance really should be within 1 or 2%. That's kind of a rule of thumb. I mean, it depends for how many iterations you run for, what's your convergence criteria, things like that. But 1 to 2% makes me happy for the most part. So that's what I was going for. Now in this model, as you know from part 1, it's forced convection through a internal fan that we used. So the inlets just have 0 pressures. That inlet has a temperature on it too. We can go into that later, but we basically have free flow at the inlet and outlet and a fan in the middle that is doing the work here. So now, in terms of meshing this aluminum box that goes around the electronics, I mean, generally the goal is to save as much mesh as you can while still getting good results. So this is kind of a design question, or I guess it's a CFD question really. Do you want to rely on, or do you care about conduction going through this aluminum box? Basically, air on the inside heating up this metal panel, and then having ambient air on the outside, allowing heat transfer. For this, I decided that I was going to suppress the aluminum box. I know I have it highlighted there, but I went on and suppressed it later. This means there's absolutely no heat transfer to the ambient. So here we're completely relying on heat transfer from the chips to the air, going outlet. It's a more conservative approach, and you're going to get results faster because you have less mesh there. It's more conservative because there's going to be absolutely zero heat transfer through it. So, and I mean, of course, more conservative, temperatures will be slightly over predicted, which is not always a bad thing. It's just important to know. So initial testing, once I had this thing put together, I used a cut plane on the inlet and outlet and used the bulk calculator to check the mass balance. I included this because it's actually an issue. I ran into quite a bit of trouble here and chased it for a lot of time and wasn't sure what was going on. So I actually had on the exit side 40% of the mass going in on the inlet. And that is a huge red flag, not even close. I don't think recirculation would do that, but I wasn't sure what was going on. So I mean, if this happens to you, just like my troubleshooting techniques, I'm going to tighten the convergence criteria, which is just going to make you run more iterations. I tried different advection schemes, but you should never see a discrepancy like that based on a advection scheme. And then I increased the extension lengths. I went from 5 times the diameter to 10 times, and it still was 40% off. One kind of, I guess, troubleshooting note that I noticed is that after all these changes, it was always a perfect 40% off. So I wasn't so sure what was going on. So I'll show my next slide. I actually was able to identify the problem. So inside that transparent square block, I have my internal fan, which is a material in CFD that we assign instead of using the actual fans and rotating regions. And I had modeled it so it was pressed up completely against this aluminum heatsink. So I didn't even think about it at the time, but basically on the outlet side, because of how the internal fan is modeled or coded basically in our CFD solver, it was blocking probably 60% of the cross-sectional area there. And that's where our mass imbalance is coming from. So I guess the takeaway here is, I didn't even care remotely about my results or what my chip temperatures were until I had this mass balance figured out. You kind of have to do these things in steps, or else you can really take yourself for a loop here. So I figured this out and was happy with my results next. So the next thing I did was look at energy balance. Basically, I just did m dot CP delta T here on the inlet and outlet. Now this is a super macroscopic approach, but it's a great sanity check here. So I have my my mass flow rate. I got the specific heat of air there, and my delta T was like 7.9 degrees C. So I had basically 8.1 versus 8.89 watts, which was a 8.9% discrepancy, which is actually a little high to me, but it's not something I'm going to throw my hands up and really go crazy. This was a auto-sized mesh, which is really generally pretty coarse, especially for electronics where we have heat sinks and stuff. An auto-sized mesh, and it auto-converged in 182 iterations. That's with the default convergence criteria. I was pretty happy and impressed to see 8.9. As you tighten that mesh up and tighten the convergence criteria, that's going to go way down. So that's good. Another point to touch on here is that we assume the specific heat is constant here. which it really is for such a small temperature delta. It's just something to keep in mind when you're doing your own calculations. So I was pretty happy with that. The next thing I kind of started to look at was, mesh sensitivity. This is our general practice here. I'm sure a bunch of folks are familiar with this. I start with an auto-sized mesh. I always use surface refinement. It's great for electronics because it increases your chance of getting a successful mesh. It looks at the smallest edge lengths up against surfaces and bases the mesh more on that than the regular macro does. So a typical mesh sensitivity study is you auto mesh and then you start decreasing the mesh by 0.7. So here I wasn't grabbing the electronics because you really don't have to mesh solid parts that hard. I was grabbing the air volumes and decreasing that mesh by 0.7. And this compounds, as I'm sure you could tell on the element count there. So I was looking at basically global max temperatures and global velocities. If you're working on a really, mission critical kind of assembly here, I would probably look at specific chip temperatures instead of global. But this was kind of a quick and dirty, do I have a pretty good mesh here? It's pretty cool to notice that my element count went up by a crazy amount here, almost a factor of 10, and my results didn't really change that much. So I was looking at global max temperatures in Celsius, and it really stuck around 36 to 37.5, and our velocities didn't really change too much either, which is really cool to see. And people ask me how good of a mesh is good enough. And as you can see here, as the element count is going up, your solve time is going up tremendously. So it's up to yourself to kind of weigh those pros and cons and decide on what is good enough for you. All right. So next, I kind of tried to assemble some design questions. It said, at one inlet temperature, does my hottest chip temperature exceed acceptable range? And then also, I talked about suppressing the electronics housing, that aluminum housing box. But what if I didn't suppress that? What if I meshed it and put a film coefficient on the outside? How is that really going to rely on, or how is that going to change the overall heat transfer and temperature results here? So I figured out pretty quickly online that kind of an average chip temperature needs to be less than 75 C for a steady state operating range. So basically, so on my inlet side, I had zero pressure, but you also, of course, have to define an inlet temperature. So I started with 20 C, which is pretty much room temperature, and I identified the hottest chip in the results. There's a small one where that black arrow is it's pointing at. So 20 C, it was only 35.7 degrees C. So then not much of a change. And then if you notice, from 25 to 30, the chip temperature more than doubles, which is kind of crazy. It's definitely a red flag. And note, just a heads up here, I looked at the average chip temperature because you don't really want to look at the max. I don't know why you would look at the min, but I wouldn't want to look at the max if I were you, because that can kind of come down to some weird meshing things. The total heat generation boundary condition is going to apply a uniform, basically wattage load over each element. So if you have a pinched element or something weird that's going on in that chip, you're going to get bad temperatures. But anyway, here, it was pretty crazy to see that the chip temperature is going to more than double the slight raise in inlet supply temperature. So I found this pretty crazy, but I looked at my mesh, I ran it for more iterations, looked at the surrounding chip temperatures, and I really do believe the results. So I what's going on here is the flow pattern is changing, and we're getting a super high temperature here, which is pretty cool. So I didn't pursue what happens between 25 and 30 C, but that, I mean, that if I was really designing this, that would be my next question, because you know, obviously our criteria was 75 C. So
yeah, maybe also look at the flow pattern, like you mentioned, not just the temperatures, and see what's going on. Yep,
and I would probably, you know, really chase the mesh, but if you're getting mesh independent results, then, you know, this is really occurring. So, yep, thanks, Marwan. So next, I basically put the film coefficient on the aluminum housing. Now, a film coefficient is just in place of modeling this big ambient temperature, you know, air box around it. It's just a standard heat transfer coefficient that's used basically to model convection on the outside of this box. So I looked at the max global temperature. Now this is back with my standard 20 C inlet, and I used a 5 watts per meter squared per degree, okay? And the overall max global temperature went from 36.3 to 32.5. So there's definitely some heat transfer there. Sometimes folks in this kind of study will say, okay, if the fan were to break, is there enough heat transfer through the electronics box that this thing won't overheat? I definitely don't think this is okay in this situation, because of such a small max global temperature, but it would be cool to pursue, and it's definitely a good question to ask. So, all right, so here I have some solver settings. Just want to touch on this. I have, you know, a lot of people asking me about a bunch of these different options and all, and so it's definitely important stuff. In terms of the necessary amount of iterations, a lot of different people have different approaches, really. I really don't like to say, hey, I'm going to run it, you know, I have 5 different scenarios, or I'm running them all for 400 iterations. I don't really think that's a good approach, because those different scenarios could really be at different points in the solve, depending on what's going on. So generally, I rely on the automatic convergence assessment, which looks at the slope of the residuals to auto-detect convergence. So a lot of times when I set up simulations, I'll just put in 1,000 iterations to run, which is, you know, definitely way too many. It'll converge before then, if not something weird's going on. And the solver will kick out when it's ready. Now, when I'm just doing, you know, rough design scenarios, if I have 5 different ones, I always just go with the default convergence criteria. You know, if you narrow your design down and really want to pinpoint chip temperatures and things like that, then you tighten your convergence criteria. But it's, you know, to do it to all 5 is definitely going to waste time and resources. Next, of course, you have to have flow and heat transfer enabled. You definitely don't need incompressible flow. That's for high Mach numbers. The next question that I get, you know, most often is, should I use auto forced convection? So auto forced convection is it's a tool of basically saving resources. So what it does is, if you enable it, it will have heat transfer disabled in the solver, and it'll solve the entire flow solution until it converges, and then turn on it'll freeze the flow field, so you're not solving for flow anymore, and it'll basically solve the heat transfer side of this analysis. This is faster than doing both at once, and it's really good if you want to rely on that to get faster answers. The big thing here is that it will not take into effect natural convection or any kind of buoyancy, which is kind of a different subject. For this analysis, I didn't use a variable air because it's really a forced convection problem. But if you have a question, if you have a bigger electronics box, or if you're using doing natural convection, or if it's a mixed analysis, you need variable air, and you do not want to use auto force convection. Basically, with auto force convection, your density of air will not change, or any other fluid if you're using it with something else.
Yeah, so the basic question here, if you want to put it in other words, is the temperature affecting the flow? If the answer is yes, the temperature will affect the flow, then you don't want auto force convection. If the temperature does not affect the flow, then you do want auto forced convection. It's another way of thinking about it.
Yep. I'll put Marwan. Thanks a lot. So next here, just a part 2. And I don't have it in the screenshot, but in terms of advection schemes, both advection scheme 1 and 5 will suffice. In CFD 2018, we made ADV5 the new default. I really don't see massive differences with this application between the two. I have good faith in my results using either advection scheme for this application. So you can, it's kind of up to you. ADV5 is the newer advection scheme, but it's not a critical question. In terms of the turbulence model, I didn't see a need to change it from K epsilon. It's the default turbulence model for a reason, and I've always had great luck and great results using that turbulence model. I would really find it weird in a forced convection analysis if you had to use something else. But anyway, the next really subject to hit on here is, do I use radiation or not? Now, it's a good question, and it really comes down to, as the engineer, do I need the physics there or not? Is it a waste of computational resources, or is it really critical to have it enabled to see those effects? I generally do not use it on forced convection problems. The big reason there is that my temperature delta, is really not that large in an electronics box. I mean, I had an ambient of 20 C and max chip temperatures. Even in my later on, those cases, they were still, under 100 C, I guess. I didn't really see that as critical to enable radiation. Enabling radiation is much more important when modeling natural convection, which we can touch on next, because it's another form of heat transfer to allow basically a density variation, which is going to be your driver of flow there. And just last note here, turning radiation off will overpredict the chip temperatures and temperatures in general. Well, the temperatures of the heat generation solids, basically, because it removes a possible heat transfer method. So it saves time here, and I know a lot of folks have electronics boards that they're modeling that are much more complicated than what we did here. They're huge and have millions of elements, and I really would not use radiation unless you have to. It's great right at the end of your analysis to clone a scenario and enable it and see what happens as a sanity check. But I would not use it right off the bat. So that's what I have here for the part 2. Now Marwan is going to touch on a little recap of natural convection that he put together. Just give me a second here, Marwan.
All right, thank you so much, Matt. Need to share my screen here. Did you make me presenter? Show my screen. Okay, so here we go. Can you see my screen now?
Yes, I can, Marwan.
Okay, I want to make that. All right. So what I have here, actually, I'm going to show the PowerPoint presentation, just show a couple of images of what we have here. It's a simple electronics box. And there we go. Okay. There we go. So basically we have a housing, aluminum housing, a simple board here with an IC chip, heat sink, a couple of capacitors, some kind of power source, and just 4 little legs, pegs here attaching the board to the box. And this is a fully enclosed box. The idea here is to do natural convection. Okay, let's say this box is completely enclosed. It's sitting somewhere where there's not even, a lot of air circulating. And we want to make sure that natural convection is going to be enough to cool this thing down to where the components are not going to exceed a certain temperature. Next slide shows this in Simulation CFD here. Again, we got the aluminum housing that is airtight. So what happens when you bring this into Simulation CFD is that it's going to generate the inside air volume for you automatically because it is airtight here, fully enclosed. We assigned certain materials to these different components, and we also have to generate the outside air volume inside of CFD. So let me go into the program here. So what we did here, so this is the model as it comes in. We got the aluminum box, the air that is automatically generated, and if I hide those 3 components, I'm going to see my board with the different components on it. So what we did inside of CFD here is generate the outside air where the natural convection is going to happen. So this would be the inlet. The gravity is in the negative Z direction going downwards, but due to buoyancy, the air will rise and flow up. And if you look at the boundary conditions here, what we applied, as far as the bounding box, what we have is temperature on the 4 sides, and we're going to use that for the radiation. We used radiation in this case. In an analysis like that, you do want to use radiation because it could affect the temperatures up to 30%. So you definitely want to use radiation. That's why we apply this temperature here. A simple 0 pressure for the outlet here. And for the inlet, we're going to have pressure and temperature. So we have 0 pressure here and the same 25-degree Celsius temperature. So 5 faces have 25 degrees Celsius, and the inlet and outlet have the 0 pressure. The mesh is important here. You definitely want to have enough mesh to be able to represent the natural convection. I did not do a mesh conversion study like Matt did, but I just made sure that the mesh looked correct and the results do look like what I expect them to. Another very important aspect here is the variable air. You want to have your air set to variable. You want to see it here say variable, not fixed. Otherwise, you're not going to see the effects of the convection, natural convection, that is. And what variable means is that the density is going to change based on the temperature. So here, edit material environment to change that from fixed to variable. The other boundary conditions are some heat generations that I applied to my IC chip and the 2 capacitors and the power supply. As far as what we have in the solve dialog, it is pretty simple. It's a steady state in this case under physics, flow, heat transfer. You want to leave this unchecked, definitely, because this is going to calculate the flow and the temperature at the same time. And I checked radiation, and I made sure that my gravity direction is set in the proper direction. It's a minus Z direction in this case. Everything else is pretty much left to the defaults. It's we enable the intelligent solution control, so it detects the convergence. And I think that is all as far as the settings. Like I said, I did change the mesh. Let's look at the mesh sizing here. It is pretty fine compared to what you would get with the auto size. And we do need that to get a nice flow, A, between the fins here, and B, just in general inside the domain to represent the natural convection. This ran, and we can look at the results here. We want to look at the plane. It's not too exciting to look at it globally, but we will actually look at the temperatures globally. And I have a cut plane over here that cuts through the IC chip. And these are the velocity profiles here. You can see that you got the plume shape that you would expect from natural convection. It's sucking air up from the bottom all the way and discharging it here at the top.
Hey, Marwan, I do want to say one thing here. Notice how, people are always asking about meshing, and notice how you cannot see any elements in the results of this plume. You can't see, triangular edges or whatever. So I think that plume looks absolutely amazing, and you have a good mesh there.
Let's take a look at that mesh.
And that's
it
why.
might be an overkill, but yeah, yeah, actually it could be an overkill here, and that's why it does look, like Matt said, nice and smooth.
But the fidelity there looks awesome.
Yeah. Okay, so let's hide that and just go to shaded here. I mean, that's the other thing. Actually, let's show we'll show it in a different plane. Let's look at the temperatures. So we're in the plane. We're going to go to result and look at the temperature. And here is the temperature. And really that IC chip is not the maximum temperature. This part here ends up being the hottest, which is 60 Celsius, which is probably still okay. Nothing crazy here as far as high temperatures. But that, of course, depends on your design criteria, if that's acceptable or not acceptable. In this case, you might want to actually add either reduce the power or maybe add a heat sink or do something to reduce the temperature if it's not acceptable. I'm going to create another plane here perpendicular to the Z direction. So rotate that. Just to show the mesh, let's go to planes, turn off the first one, like this. And let's move it down so we can look at the mesh in the heatsink. It's not too bad, actually, which actually brings up a good point. Someone might be thinking, well, it's a pretty fine mesh. If we look at the, regular, the domain, the air domain, it's a pretty fine mesh, but maybe I want a little finer mesh here between the fins. Well, in that case, refining the mesh would not really be the best thing to do. It would be better if in your CAD model, you actually maybe make this 3 separate volumes. So you force the mesh to happen between those volumes. And this is something that is commonly used just to force mesh layers to be where you want them to be and not anywhere else in the model. This will save you a lot of mesh if you do it that way. It might be a little bit of work inside your CAD, but it's not too bad. Basically creating those volumes here that will force mesh to happen where you want it to.
Yeah, that's a trick I've been pretty much using more and more. You know, when I was new to the tool, I kind of resisted that, but it's so worth it. So basically between the fin where that air domain is, you would make two separate rectangular volumes, and where it's touching, basically where those two faces, the two air volumes are touching, it forces a node there, the way the mesh works, which means you're guaranteed to get two elements, you know, one on each side of the node. And so yeah, and this is of course besides the boundary. They're basically the wall layers. So.
Yeah, so the question is it more work? Yes, it is more work. Is it worth it? Well, that's for you to answer. If it's easier or faster just to throw a fine mesh everywhere that's going to give you that definition between the fins and you don't care, then definitely that's the right answer. Don't worry about it and throw a fine mesh. If throwing a very fine mesh is going to really make the analysis go slow, then yes, it's worth it to spend some time creating those volumes and then have a model that you can run over and over again without having to wait a very long time to get results. So it's good to know that it's something that you can do available to you should you choose to go that way. Right.
And one last thing here, sometimes I see people using refinement regions on the heat sinks to get that two elements in between the fins. And I don't really like that approach because you end up, you know, you use a rectangular box and you end up really over meshing the metal fins. You know, when you're going through solids, it's just conduction. The material properties of aluminum here are not changing based on temperature. So you really can get away with a pretty coarse mesh through the metal fins. So it's just a waste of resources, and I would prefer to do it in CAD.
Yeah, as easy as a refinement region is and useful as it is, sometimes it could be an overkill that doesn't give you the amount of control that you actually need, the fine tuning that you may need, such as in this case here. Just between the fins and not the fins themselves. That box is not going to give you that fine control.
Okay. One other thing you can do here is turn on gap refinement. It's basically going to help so you don't transition from too coarse to too fine of a mesh. It basically spreads the seed points at a more conservative length and ends up putting more mesh in there. Chances are you're going to get a better mesh in between those fins when using gap refinement there. So cool.
Yeah. So yeah, anytime you have fins like that, you want to pay attention, or any narrow passages, you want to pay extra attention to the mesh. And definitely with natural convection, you do want to have a certain amount of mesh to be able to represent what is physically going on.
Cool.
Yeah, I think that's all we have here for today. Do we have any questions?
Marwan, I'd like to touch on one last thing with the natural convection. There's two different things. I usually spend a lot of time looking for recirculation. Generally, it's going to be across the outlet because your velocities are so low in natural convection, and by the time you're at the outlet, the temperature differences are pretty low. So generally, I drop a plane in there like that, or across the outlet, I guess.
Even on the outlet?
So I drop it so it's with the Y, so we can see it from, yeah. Right. I mean, you don't have to do it, but this is how I would, and then basically enable velocity vectors. And,
okay.
And look at that outlet. Side, we gotta, you gotta fix that.
A bit too big, maybe a little more arrows here.
Right. I mean, there's like, I see like two that face down, but in general, they are all going in the right direction there. It's probably an anomaly on the corners.
Mhm.
So, but if you're seeing a big time swirl across, that's a big problem there. So the other thing I wanted to touch on is basically picking between turbulence models. It's fine to use K epsilon. Some people in this application use mixing length, which is going to produce a less turbulent flow. It could be, for your application, a little more, it could definitely be more accurate. And just remember, if you choose to use mixing length, you're going to have less turbulent flow around the electronics, less convection heat transfer, and probably some higher chip temperatures there. So I see people use both, kind of depending on the application there. So.
All right. Thank you, Matt.
Yep. So I guess now we can open it up to questions. I know we've had some people asking questions all along. You could just drop them into basically the question box there. We'll get them and try to answer them the best we can. Marwan, someone asked me to show how to check the mass balance. So.
Well, for the mass balance, it's probably easier to do a couple of planes here.
I'm happy to do it on. I think they were asking about my model.
Sure.
I'm happy to take over presenting here.
Yeah. Let me make you the presenter here. There you go. You should be able to share your screen at this point.
All right, Marwan, can you see my screen?
Yes.
All right, so results here. Let me get rid of all my planes. I already have them there. But so basically, in results under planes up top here, I'm going to say add. So this one was already dropped into the X plane. So I'm going to move it towards the outlet. Your question of how far towards the outlet is kind of qualitative. You have to decide that on your own. I like to go pretty close, but not right at the outlet. So say maybe that's good. And there is a bit of a temperature gradient there, which is, I was staring at that for a while, but I think I can live with it. When we use the bulk calculator, we average the temperature over the area there. So anyway, up in the right-hand corner here, we have the bulk calculator. So while in planes, while I have this specific plane selected, I hit bulk. Basically, I'll look at mass. I guess I can use grams per second and do temperature. Calculate. So I don't worry about the negative or positive, whatever. I have like 1.12, roughly 27.89 C. Let me drop in another plane, put it in the Y. Just going to do the same thing here. So 1.11, which is pretty close. I think that's what I had in my slides, and of course 20 C, because that's our boundary condition at the inlet. So you want to make sure that's at 20. So this is how I do it. If you have planes that intersect different volumes, you can basically on my mouse, it's the scroll button to select that specific one. It'll highlight the different cross sections. it'll do it right here and grab it. So you can see there's none by default. It's already grabbing it, but you can see it's starting to highlight on the screen there. So Marwan, you have anything else to add here?
No, nothing to add here. That's how you do it with those planes. I got a couple of questions here also. Do we ever run into issues with pressure and thus convergence in regards to the sealed box within the natural convection domain? Typically, we don't. If the mesh is fine enough to capture the flow, typically the pressure is not an issue.
Yeah, I think that's something that occurred. I mean, I think I did face that, but I was using quite an outdated version of CFD. There's different little tricks there. It's been a while, but I believe at one point I put a zero pressure on a solid on the inside. I guess it's something to try. If you've tried all else and you're convinced that this is a solvable problem because you have two different completely separate fluid domains, probably not a bad idea to reach out and ask for some help or something.
Yeah, I see what you're saying. So since there's no pressure reference inside the sealed box, is it going to have a hard time honing in on the correct pressure? Right. Yeah. So what you do there by assigning a zero pressure, just give it a reference at a solid that's then going to be interfering with the flow or the pressure distribution.
And we have someone asking about mixing length versus K epsilon. Basically, the K epsilon is just going to be a lot more turbulent at really low velocities, which may not be accurate. You may have, laminar flow inside of some areas of your electronics box. The K epsilon is going to make everything turbulent. So, when we do natural convection studies, we look at the, basically the max velocities. You're generally going to see, I guess probably 20 to 30 inches a second is a high velocity, at least that ballpark. That's a pretty slow flow there, and at times mixing length can be more appropriate. I usually end up trying both and looking at the results. There's other webinars on turbulence models. I could dive more into it. There's also help articles and stuff. So if you want to look into that content, it's definitely out there. I just Google search it and reference it sometimes. What helps there is that I can bookmark a web page and go back to it a million different times. So that's it from me.
One last question we have here is, why not emphasize mapped mesh for the heatsink? I suppose that means extruded mesh. Well, the extruded mesh only works for when you have the beginning and end surfaces identical, which is not the case for the air volume between the heatsink. It may be for the heatsink itself, but not for the air inside of it. But it's something to try, sure.
It's if you were going to break those air volumes up like we were speaking about in CAD, you'll be able to apply an extruded mesh there because you can identify two different ends that have the exact same surfaces, basically. So
that's right. All right, I think that brings us to the end, Matt.
Nice. Thanks a lot for everybody that's attending. We're going to upload this to YouTube, and we'll have a box link with our slide deck so you can reference that and our support files. So we can, you guys can reference that later on. So.
All right. Thank you, Matt. And thank you, everyone. And I hope you will join us again for our upcoming webinars for CFD and any other topic that you might be interested in.
Awesome. Thank you.